Alright, so we're going to continue where we left off last lecture. We're still in chapter 20, and we're talking about these reactions of alkyl chlorides, which could be like acid chlorides or acid bromides. And we were getting into reactions with organometallic reagents. So those collectively would be like Grignards, organomagnesium, organolithium, so magnesium, lithium, and then cuprates are your kind of new one that we've seen a couple times now. Alright, and so let's just show that one more time. I'll just have this random organolithium. And the idea, we'll pick some Grignard, or it could be an organolithium or a organomagnesium, which is a Grignard. Let's just pick, I don't know, ethyl magnesium bromide, followed by water, or ethyl cuprate. Followed by water. Right, so that's when I say 2 carbons parenthesis 2, that suggests the structure of this is copper negative lithium plus, or also Et2 copper lithium. Okay, ethyl cuprate. All right, so what happens in the top case? We showed this last time. It reacts once. But with Grignards, it attacks twice total. So ethyl attacks once to make the ketone, then it attacks again to make the tertiary alcohol. But the cuprate, the difference between the Grignard and the cuprate is the cuprate only attacks once. So you stop at the ketone. That's it in a nutshell, okay? How do we make a cuprate? So you make them from an organolithium. So if I want to make diethyl cuprate, you would start with the ethyl bromide, react with, and it's usually like 2 of these plus plus lithium makes 2 ethyl bromides, and then you react it with copper iodide, and that gives you that diethyl cuprate, or Et2 copper lithium. Okay, great. Sorry. All right, so that's how you make them. What was the other reaction that you learned about with cuprates previously? Was that they do conjugate additions. They do 1,4 additions. Let's just show that real quickly for review. So I'll show this example of cyclohexenone, where it's the alpha beta unsaturated ketone. Cuprate attacks, and you get that's the product after workup. I'm not going to do the mechanism, but it was really easy. Ethyl attacks there, push electrons, and then the second step, it swings back, grabs proton. So we did that not last time, but kind of recently. And then, of course, with the Grignard, I switched it to phenylgrenadier this time, but the same thing happens except it attacks the ketone and not the alkene. And you get the benzene attached and to make a tertiary alcohol. So that's kind of like, those are the two situations for cuprates. I think that's all you learn about cuprates through the end of Organic 2, is that they do conjugate additions, and they also attack acid chlorides and give you ketones, which is what we just saw. Okay. Okay, and let's see, the other, something that's kind of related to this is we can do another reaction of acid chlorides, we'll call F, partial reduction of acid chlorides. And just like we can do a partial nucleophilic attack with a cuprate, we can also do a partial reduction. And so here I will show some random acid chloride, and what I'll do is I'll show the two kind of pathways you can do. One is using lithium aluminum hydride. Of course, that is a super strong reducing agent. Lithium aluminum hydride is a super strong reducing agent. That will attack once to make an aldehyde. Of course, mechanistically it's like H minus, electrons go up, electrons go down, kick it off, right? Yeah, so that makes sense, how you get an aldehyde. It's an NAS reaction, right? NAS. Nucleophilic acyl substitution. But then, of course, aldehydes react again. And you get a alcohol, right? Yeah, so H minus attacks again, electrons go up, and you get a primary alcohol. It's a primary alcohol. 1, 2, 3, 1, 2, 3 carbons off the benzene. Okay, so just like we have, using a cuprate, we could get a single addition of a nucleophilic carbon. There's also a different reducing agent which gives you, it stops at the aldehyde. And that special reducing agent is lithium plus H aluminum, and it's 3 terbutoxys. So it's and there's a negative charge on aluminum. It says lithium plus H, Al minus with 3 terbutyls. I think it's called lithium triterbutoxy. Lithium triterbutoxy aluminum hydride. Lithium triterbutoxy aluminum hydride. Yeah, lithium triterbutoxy aluminum hydride. And it's water. And it's just a weird reducing agent that kind of captures the aldehyde intermediate and does not reduce the aldehyde, so you get an aldehyde product. Okay, so it's a specialized reducing agent. Specialized reducing agent. Okay, cool. And so we have a specialized, like copper, the copper is like a specialized organometallic that gives you a single addition. And this lithium tributoxy aluminum hydride is a specialized reducing agent that gives you a single addition. It doesn't keep going, it doesn't reduce the aldehyde. Okay. Just another example. Remember that lithium aluminum hydride, if you have an alpha beta unsaturated functional group, it does not attack the alkene, whereas other things might. The lithium aluminum hydride just reduces the acid chloride twice to the tertiary or the primary alcohol, water. So it attacks once to kick off the chlorine, attacks a second time, and you get the primary alcohol. But if we do this weird reagent again, lithium plus HAl and water, then it stops at the aldehyde. All right. Cool. I'm going to provide a summary sheet. I usually give it with the exams, but we don't really have exams this semester. But what it's going to show you is a very nice kind of summary of like the 4 different things you can do. One is kind of like RMGBr, R2 copper lithium, lithium aluminum hydride, and then now we have lithium plus HAlO tripbutyl 3. To keep these kind of straight in your mind, I have little summaries that I'll provide. Because this isn't going to be the only situation where we have this. Esters are going to have something kind of funny like this too. So anyway, what are the products? Well, Grignard attacks twice to give you the tertiary alcohol. The cuprate adds once to give you the ketone. The lithium aluminum hydride reacts twice to give you a primary alcohol, and this selective reducing agent that only reduces once would give you the aldehyde. Okay, so you're going to see this for other functional groups, and I'll give you some little guides that help you keep this organized in your mind. Okay. All right, number 6. Moving on, chemistry of carboxylic anhydrides. So these are typically not something we make. But we use them all the time, kind of commercially. So we can purchase a lot of these anhydrides commercially. It's not something we really create though in research, or most laboratories don't really make anhydrides. But what are some of the common ones? Common ones are that one, which we saw before, acetic anhydride. kind of like a derivative of acetic acid. This one is kind of a cool cyclic anhydride called succinic anhydride, or succinic anhydride. And then if you extend the carbon and make it a 6-member ring, with 3 carbons, carbon, carbon, carbon. Here's 2 carbons. This is called glutaric anhydride. So these are commonly used anhydrides. I'd say acetic anhydride is definitely the most commonly used one around the world, and it's actually how we make aspirin too, commercially. Okay, so how do we making an anhydride? I'd say the acid chloride method is actually pretty useful. So of course, if you have a acid chloride and a carboxylic acid, you react with base. Okay, and this is you know, when we do these reactions in the presence of base, we say it's base mediated NAS, base mediated NAS. Usually the nucleophile attacks, and then you lose a proton afterwards, and then the intermediate collapses. But if you have an acidic functional group like a carboxylic acid, then the base actually takes the proton first. Right? Because the pKa is really low for a carboxylic acid. It's like 4, I think, or something. And anyway, so what happens is the base takes the proton first, and now it's really straightforward. Nucleophile attacks, and there's your tetrahedral intermediate. Tetrahedral intermediate, and then the oxygen kicks down, breaks off the chlorine, and you're done. Okay, so other base mediated NASs, the nucleophile attacks first, and then the base reacts. Okay, typical base again is pyridine, PYR dot dot. Okay, all right, so that's one way to make anhydrides. One of the things you do, probably the most common thing you would do with an anhydride, is using, what would you use an anhydride for? To make esters and amides. That's what generally anhydrides are used for. So let's show a couple examples. Okay, acetic anhydride, some amine, maybe a little base. Creates the amide. Okay. What's the mechanism of this? Like I said before, if you have a poorly acidic nucleophile, like amine, the base does not react initially. What actually happens is the nucleophile attacks first. Okay, and now we have a plus charge nitrogen, right? Now you have a highly acidic proton and the base takes it off. B dot dot takes the proton off. Okay. So usually we lose a leaving group. So where's the leaving group? This is the leaving group. This whole thing is the leaving group now. Okay? And so the O minus swings back and kicks off the leaving group. And that gives a product. Okay? So that's an example of using an anhydride to make an amide. It's very similar to acid chloride. The only difference is the leaving group isn't Cl, it's this whole thing. It's a resonance stabilized leaving group, right? Your byproduct is acetate. There's an O minus, C double bond O, CH3, okay? All right. Ester, or if you have an alcohol and react with acetic anhydride, alcohol with acetic anhydride makes esters. Great example, whoops. Is the synthesis of aspirin. That's a carboxylic acid on top. But yeah, this and we can either do this with a base. Sometimes you can do it actually without a base. But essentially, as a mechanism, it just attacks. Electrons go up, electrons go down, and this gets kicked off. So yeah, that's how aspirin is synthesized, using acetic anhydride on commercial scale, like multi-ton scale. Okay. Alright, so now we're on to esters. We're on to esters. Remember our initial little chart we had. Well, we're kind of moving from left to right. I don't know if you noticed that. Acid chloride, anhydride, esters. Next we'll talk about amides. And then carboxylic acids, that was the last chapter. So we're kind of going left to right. And with acid chloride being the most reactive thing, and there's a little less reactive, less reactive, less reactive, at least reactive. Okay, so we're on to esters. Conceptual details were covered in the PowerPoint. How do we make esters? There's kind of three ways we can do this to create esters, to make them. Number one is from acid chlorides. Of course, this totally makes sense. Any acid chloride can react with, like, alcohol. Maybe a base like pyridine, and you can imagine that the alcohol attacks and you make an ester, right? Methyl benzoate, the ester, okay? This is all base mediated NAS. Base mediated NAS. You should know that mechanism, okay? Number two. by the Fischer esterification. So you can, we did this already, I'm not going to repeat the mechanism, but let's make the same ester by the Fischer reaction. This time you use a carboxylic acid and methanol, catalytic acid, and out comes the same ester. Okay, and we did that mechanism. This is all reversible, and it's not base mediated NAS, it's acid catalyzed NAS. Acid catalyzed NAS. Protonate the carboxylic acid, alcohol attacks, etc. Okay. We actually have a third one, which you have not learned before. It's really easy though. Number 3 is by Sn2. By Sn2 reaction. You actually have learned about it a little bit in Organic 1. That's crazy because I don't know if you remember any Organic 1 stuff, but such a long time ago. But yeah, you did actually learn a little bit about the Sn2 synthesis of esters in Organic 1. So let's see an example. You actually probably learned about it a little bit in the Sn2 chapter, a long time ago. So another way to make esters, I'll convert this carboxylic acid into an ester. Is simply to treat it with a base, which is just going to rip off the proton. Bases take protons off acidic functional groups, and then just throw in an alkyl halide, maybe a DMF. Why DMF? Because DMF is an Sn2 solvent. It accelerates Sn2 reactions. And this is a way to make esters using the Sn2 reaction. Okay, so what's the mechanism? The base is NaOH, or OH minus. Rips off the proton. To make a negatively charged carboxylic acid looking thing. You guys remember the name of that? It's not carboxylic acid anymore, it's called a carboxylate. Okay, and the negative charge here is just a nucleophile. So why did we do this step 1? Because to make things more nucleophilic, it's better if they're charged. So OH can be a nucleophile, but O minus is a much better nucleophile because it's got a full charge on oxygen, right? Okay, so as a good nucleophile, what's it going to do? It's going to react with the electrophile. Delta minus delta plus. So this is just a plain old Sn2 reaction, right? The O minus attacks the plus charged carbon. And that's it. That makes the product. So it's actually a really easy mechanism. And yes, you can make esters by Sn2 reactions. Okay? There's another thing from Organic 1, kind of related to this, that we when we teach you this in Organic 1, we always say, oh, well, some of this you can't learn until Organic 2. And it's the idea that if I want to do an kind of like an Sn2 reaction like this, like if I was trying to do this, convert the Br going away, it's an alkyl halide with Br going away, and I want to react it with something to invert the stereochemistry, right? OH. You would think, oh, this should be really easy. This should be really easy, right? I mean, if I think about it, I'm just replacing the oxygen, the bromine with an oxygen, so I could just do OH minus, right? And that would, you would think, attack and kick off the Br and make the secondary alcohol chiral and inverted, right? But it doesn't work. Why doesn't it work? Because what actually happens is it does this is Sn2 up here, right? The problem is hydroxide is actually a pretty good base also. So what rather happens is you get E2 products. Okay? And so you probably remember something about that from Organic 1, that in order to do an Sn2 reaction, ideally your nucleophile is not a super good base, because when you have a basic nucleophile, sometimes the elimination competes. Anyway, so there is a good way to do this though. And this is what we teach in Organic 1, but you don't have enough information to know the full story. Now you do have enough information for the full story. So this is actually a couple-step process, and yes, you did learn it in Organic 1. It's at least in the book, and I teach it in my Organic 1 class. But the idea is, rather than use a basic nucleophile like hydroxide, why don't we use a non-basic nucleophile like carboxylate? And we do it in DMF or something. Nice Sn2 solvent, right? So have it attack. Okay, and so that's an Sn2 reaction with inversion of stereochemistry, and it actually makes that. Well, that's not the same as this though. And in Organic 1, we teach here, and then we're like, okay, there's some magic step that cleaves the ester and makes a alcohol, right? So we didn't know how to do that, but now we do. We just learned it, right? This chapter. How do you convert an ester to an alcohol? And of course the byproduct is the carboxylic acid. It's saponification, NaOH, right? Saponification. Base-mediated ester hydrolysis. Saponification. I didn't spell it. Yeah, I spelled it right. S-A-P-O-N-I-F-I-C-A-T-I-O-N. Saponification. So that cleaves the ester to the alcohol and the carboxylic acid. The mechanism is hydroxide attacks, and it's a couple steps, but hydroxide attacks, electrons go up, electrons go down, kick off. H3O is involved. The other way to cleave an ester is we call it the reverse Fischer reaction, which is essentially just cook it in acid water. It's the opposite of the Fischer's, the opposite mechanism. So the ester plus acid water, cook it, and then out comes the same products. It's the Fischer reaction going backwards, okay? Anyway, so now you know how to do that. Okay. All right, so we're still on esters, number 7, esters. Another reaction of esters is hydrolysis of esters. We just saw that actually in that last example, that you can take an ester and treat it with acid, H3O plus, or you could draw it this way, with the ester plus water, acid catalysis, H plus, catalytic acid, and then that would make a carboxylic acid and the alcohol. I'm not going to review that. Reverse Fischer. You can step through it. It's the opposite of the Fischer. Protonate the ester, water attacks, PT, etc. And also, of course, the saponification method. This is a one-way arrow, NaOH, followed by acid. So we just did this also, I think, last chapter, without doing the whole mechanism. Electrons go up, down, off, and then there's a little bit more to it. That's essentially it, though, how hydroxide is a nucleophile and attacks. So see last lecture for a little more detail on this, on the mechanism. Okay, so yeah, esters are easy to hydrolyze. That's the point here. Okay, by acid method or base method. Okay, esters can be converted to amides really easily. Remember our little chart where we go acid, chloride, anhydride, ester, amide, carboxylic acid. How ester to amide is going right way, and it's always easy to go from something on the left to something on the right. So ester to amide is very easy. This is called aminolysis. Aminolysis of an ester. And let's show an example. A little bit of heat. Okay, so this is incredibly easy. We're going on the little chart. We're going from left to right, and it's just so easy. We don't even need to add a base. No base added. Because what helps is this happens to be a base itself. This is a nucleophile and a base, right? And so it just attacks as a nucleophile. There's your tetrahedral intermediate, and then it's going to act as a base. Act as a nucleophile, now it acts as a base. Takes off the proton, makes a different tetrahedral intermediate. Collapse to the product. So you could call this base mediated NAS if you like. The only funny thing is that we don't actually add a base like pyridine. We don't need a base because the nucleophile, the amine is a base itself. Okay. All right. So very nice. So that's a reaction of esters to synthesize amides, called aminolysis. Okay. One more I'll just show as a quick example. You can also same exact idea. But if I react methyl benzoate as an ester, if I just use ammonia as a reagent, that'll convert the ester to a primary amide which has an NH2 on it, and it's the same exact thing as I just showed up here. I'm not going to really step through it except the first step. Essentially, electrons up, down, off. Electrons go up, down, off. And here, just as well, the NH3 is a nucleophile and the NH3 is a base. It's a base and a nuke. So the NH3 will assist as a base. First the NH3 attacks, then it acts as a base to take off the extra proton, collapse, and you form the product. Okay? Okay, so moving onward, more esters. They react with organometallic reagents, just like we saw with cuprates. Remember cuprates? Cuprates would act with Grignards to do a double addition, and they'd react with cuprates to do a single addition. Esters don't do that. They only add once. Sorry, only Grignards attack them. R minus only. Sorry, I'm saying it wrong. R minus only attacks twice. And the R minus, the thing that's doing the attack is a Grignard, R MGBr. Or organolithiums. Remember, in most cases, a Grignard, R MGBr, is synonymous with the organolithium. They both do the same thing. And there's no cuprate attack, no cuprate reaction with esters. Okay? So cuprates will only react with acid chlorides to do that kind of mono addition thing. Okay, so let's just show an example. If I react this methyl ester with, we're going to pick a Grignard, what should we use? We'll do phenyl Grignard. Okay. It attacks twice to give the tertiary alcohol. And the mechanism is super easy. It's NAS. It's base-mediated NAS. To give a ketone. And then what happens when a ketone sees a Grignard? Then it reacts to make an alcohol. So now the Grignard attacks again. You get a tertiary alkoxide. So the tertiary alkoxide, kind of like a tertiary alcohol, except it's not quite an alcohol until you give it a proton, and then it becomes a tertiary alcohol, right? All right, so yeah, and there's MGBr here. Yeah, so Grignards attack esters to give tertiary alcohols. And there's no simple way, how we did it with cuprates, to just add once. Cuprates don't react with esters. They only react with acid chlorides. Okay? How about this? So this is a cyclic ester All right, and we're going to react it with methyl Grignard, CH3MgBr. Remember, when I do Grignards, one way to draw them is like CH3 dot dot minus MgBr plus. That's sometimes useful for the for the mechanism, because you can sort of circle the lone pair. Okay. Anyway, we could have done that up here also. We could have said, we could have drawn it as benzene dot dot minus and then have it that attack. Well, anyway, I'm not going to do this one for you. 1, 2, 3, 4. 1, 2, 3, 4. I'm going to let you try to figure out the mechanism to how this tertiary alcohol is made. Mechanism, question mark. Maybe as a nice quiz mechanism, I don't know, see if you can do it. Methyl attacks, electrons go up, then it kicks off, breaks off this as an O minus, and then you have a ketone, and then the Grignard attacks the ketone, and then you get a tertiary alcohol. See if you can figure out the mechanism from this cyclic ester to this acyclic tertiary alcohol and primary alcohol. One other thing, a cyclic ester has a name. Cyclic esters have a name. So cyclic ester, which is an ester that's cyclic, has a name called a lactone. Lactone. So lactone, if you ever hear of a lactone just means a cyclic ester. Okay? Alright, see if you can do that mechanism. So we did reactions of esters with nucleophilic carbon, right, Grignards. Now let's do reactions of esters with reducing agents. Now this, like if we talked about the nucleophilic carbon, Grignards, we said that R minus attacked twice, right? It attacked once, it attacked twice. But we didn't have R minus attacking like a cuprate that would only react once. So with esters and reacting with reducing agents, there are going to be two different versions. I'm going to call H-2 equivalent, H-1 equivalent. So esters can react either twice or they can react once, depending on the reducing agent you use. Okay. What is the super strong reducing agent that we've seen 1,000 times for like ketones or carboxylic acids? It's not NABH4. It's another H something. It's going to be LiAlH4. LiAlH4. So lithium aluminum hydride is the super strong reducing agent for a lot of things versus like NABH4, right? NABH4 is a wonderful reagent. It's very stable, and we actually use it in Organic 2 lab to reduce ketone. It's not insanely explosive or flammable, whereas lithium aluminum hydride will blow up the lab if you do this wrong. If you do the reaction wrong, or if you kind of mess up the procedure, you could start a big fire with lithium aluminum hydride. You have to be very careful with this stuff. This stuff, you could almost do anything and it won't catch on fire. So this stuff you can be a little more, I don't want to say careless, but NABH4 is a relatively stable reducing agent. Okay, so lithium aluminum hydride is a double reduction. This one you've never heard of before. It's going to be called dibal. Dibal or diba. It's DIBAL or DIBAH. It's the same thing. And it's going to be a partial reduction of a ester to form an aldehyde. Okay, so let's first show the top one. And we're going to react ethyl ester with lithium aluminum hydride, maybe some acid water. Okay, So this is very straightforward. And it reacts first to make an aldehyde, and it keeps going to make the alcohol. This is basically organic 1 stuff, except the first step's a NAS reaction, and I'm not even going to do it because it's so easy. The way to do the mechanism, though, is to remember that lithium aluminum hydride is kind of like H negative nuke. I just call it that. It's a nucleophilic H minus, nucleophilic hydride. Remember that H minus is hydride. H plus, if you have H plus, it's proton. So H plus is a proton, right? H minus is hydride. So you have nucleophilic hydride, and essentially the mechanism is up, down, off. And that is an NAS mechanism to give the aldehyde, and then that is a highly reactive functional group, and that reduces again to the primary alcohol. Okay? So now for the partial reduction, and by that I mean R minus 1 equivalent. Sorry, I said R minus. Look above, it says H. It should be H minus. H minus 2 equivalent, H minus 1 equivalent. So let's erase R minus and write H minus. H minus 1 equivalent is a partial reduction. And what did we say it was? It was a 5-letter thing. Dibol or dibol. Same thing. I guess when I learned organic chemistry, I started calling it dibol. A lot of books call it dibol with an H at the end. Okay, and let's show what the reaction is, and we'll explain how it works. So there is a methyl ester. Okay, and dibol. I'll explain the structure in a second and how it works. It's going to give you a single reduction to the aldehyde. Okay, all right. And how does it work? How does it work, and what is it? Okay, so dibol is just another aluminum thing. It's it's basically a different H minus. It's going to be a slightly different H minus reagent. Okay, oops, all right. So what is this different H minus? It's HAl. It's diisobutane. So these things, remember this from organic 1 maybe, branched substituents. These are called isobutyl groups. So you have 2 isobutyl groups. 2 isobutyl groups, aluminum hydride. And what might that be called? Diisobutyl aluminum hydride. Diisobutyl aluminum hydride, and that explains dibol or diisobutyl Al it's another abbreviation. So dibol or dibol. Okay. And it's essentially just another H minus. It's H minus. Okay. So H minus, nucleophile, what's it going to do? It's going to attack the same way. There has to be a twist to this on why it stops once, right? It stops the aldehyde, doesn't keep going. So how does that happen? Well, nucleophile attacks. Let's draw it out now. You got O minus, OCH3H, right? And the way I draw this now, you have a counter ion, and it's Al plus with those two isobutils on there. So it's Al plus and then two isobutils. Okay, let's put some brackets around there. All right, cool. So that's your tetrahedral intermediate, right? And something crazy occurs here. Usually what happens to the tetrahedral intermediate swings down and kicks off a leaving group, right? Well, this one's a temporarily stabilized tetrahedral intermediate. A temporarily stabilized tetrahedral intermediate. Okay. It does not collapse. It does not collapse, okay? However, when you treat this with water, then what happens? Well, then the O- gets protonated, right? So the second step, remember it's a two-step process. You do Dibol, makes this, then you do H3O. What does that do? That protonates the oxygen, and that actually makes that allows collapse to the tetrahedral intermediate. So let's draw just that now. H3O makes what? Okay. And this falls apart now. Kicks off the ester, the alcohol, the methyl alcohol. And that gives you the product. We lose a proton in that step also. But that is how Dibol works, and how you get a partial reduction, right? It's just a funny aluminum hydride, diisobutyl aluminum hydride. H- attacks, just like always. But now instead of the electrons going up then kicking off, they don't. You have a temporarily stabilized tetrahedral intermediate, and then the O- grabs a proton, and then now your tetrahedral intermediate falls apart, kicks off methyl, and you make the product. So that's the key difference between this and lithium aluminum hydride, because lithium aluminum hydride, it attacked and it just did everything immediately. Electrons up, down, off, makes an aldehyde, and then H- attacks again, and you make the primary alcohol. So that's the mechanism for how Dibol stops at a single reduction. Okay, cool. All right, great. Okay, so next, related to esters, another reaction is a pretty easy one. Alkylation of Ester Enolates. So we know enolates from ketones and aldol reaction and all those things. So alkylation just means attachment of something to an ester enolate. So let's just show an example. It's really easy to understand. So we have a cyclic ester. What do we call these again? Something ONE. It's called a lactone. LACTONE, lactone. Okay, so if we treat this with a super base and then a alkyl halide, what do we get? We will get an alpha alkylated product. Okay, and what's the super base we always use? Well, for most of these things, if we want to deprotonate an alpha position, it's LDA, which is lithium diisopropyl amide. I'll draw it down here, what it is, LDA. So LDA is nitrogen, isopropyl. dot dot negative, well dot dot on both sides, negative, lithium plus, like that. That's LDA, right? Yeah, it's a sort of complex between these two things. Lithium diisopropyl amide. Why is it called an amide? It doesn't make any sense. It's not an amide, right? Well, the N- things are called amides. It's not like the normal use of the word amide. Anyway, it's a super base. It'll deprotonate easily under pKa like 30 or so. So what's the pKa of a ester? It's like 25. pKa is like 25. So if it deprotonates under 30 and the pKa here is 25, it's like no problem. It'll just take it right off. Also, what's the pKa of a ketone, just for comparison? So what's the pKa of a ketone? That's like 20. So yeah, these kind of protons, LDA just takes right off. pKa 25 or pKa of 20, LDA is a good base. Okay, so what's the mechanism? It just grabs the proton. Take the proton off. Okay. And it makes an enolate, right? Base takes the proton, kicks the electrons in to make a C double bond O. Oxygen, electrons go up to the oxygen. Okay, now what do you have? An ester enolate. So it's just like an enolate, but it's an ester enolate. And now, incredibly simple, this just swings down and attacks, kicks off the leaving group. This happens to be a kind of a weird Sn2 electrophile where we attack kind of the left side. It's sort of like an Sn2 reaction, but in this case, since the leaving group is next to an alkene, we actually attack the alkene to get the product. Generally speaking, though, it's just an Sn2 reaction, right? So if I have this and I go you know, it's like this. Like that, okay? Yeah, this just happens to be a little bit of a weird electrophile, so it attacks from the alkene. Generally speaking, though, if you even like on an exam or a quiz attack that carbon and kick off the leaving group, it gives the same product, even though this mechanism is a little more correct. So I wouldn't stress about this situation. You can just assume that it attacks the carbon, kicks off the leaving group, and then the product's the same. Okay, so that's alkylation of an ester enolate. And we're using LDA as the base. LDA takes off the proton, makes an ester enolate, and then attack an alkyl halide and gives the product. Other thing, that was F, alkylation. Two more little things. Esters in nature and like food and biological membranes and all that kind of stuff. That was in the PowerPoint, PPT. And spectroscopy of esters. That was also PPT. What's PPT? PowerPoint. So the PowerPoint slides we did earlier, that's kind of the G and H topics. some of the relevance and spectroscopic features of esters. Okay, NMR, remember NMR will be a fun one potentially on the quiz. Okay. Okay, so we're done with esters, let's go to amides. Amides. Alright, so how do we make amides? First of all, how do we make them and what can we do with them? We make them, usually the way I like to make them is we'll say from a more reactive derivative. By reactive, I mean, remember our leaving group chart where we went from acid chlorides, anhydrides, esters, etc. Yeah, so we could just say, like, if I want to make an amide from a acid chloride, that would be really easy. Maybe use some pyridine. Right? Carbon, 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 carbon. And this is base mediated NAS. Or if I want to use an anhydride, like acetic anhydride, incredibly easy. Same idea. Also base mediated NAS. Nitrogen attacks, electrons go up, then you take off the proton, and then it collapses and falls apart and you get the product. Okay, so base mediated NAS is a wonderful thing and it makes all sorts of amides and things like that. Okay. Amides and esters are made really easily from this base mediated NAS from like a acid chloride or anhydride. Okay, so how about hydrolysis? Like, can we convert an amide to a carboxylic acid? So yes, you can. And so if you treat a amide with acid water, you get the amine and carboxylic acid. So this degrades. This is essentially same mechanism as reverse Fischer. Fischer was an ester reaction, and reverse Fischer was the acid catalyzed hydrolysis of an ester. But this is the same mechanism and everything, and I'm not going to do it because it's just kind of silly, and it's, you know, protonate and then water attacks, proton transfer, make a good leaving group, kick off. So it's, you could do this. I would say it's not that exciting of a mechanism. Okay. I'll say it's very harsh. This is a very harsh reaction. What do I mean by that? It's very slow. Amides are super stable. We talked about that. Amides are stable. Very stable. Amides are very stable due to resonance. We saw that in the PowerPoint. You can draw the resonance structures that really stabilizes amides. Amides, fortunately, they are stable like in our body, which are all of our amino acids and protein linkages are all amides. And if amides were a very easy to hydrolyze thing, then our body would just fall apart, right? It's kind of fortunate to us as a living organism that our amides in our body are actually kind of stable, just like this amide is kind of stable, okay? You can also hydrolyze an amide through the same mechanism as saponification, like saponification of ester, and it's also very harsh. It's not a fast reaction. It might be high temperature, you know, high temperature. Top one's high temperature also, right? And yeah, but the mechanism is easy to draw. It's just not that exciting. It's just like saponification. So yeah, electrons up, electrons down, electrons kick off the leaving group, and that's essentially what saponification is. And it's a very harsh reaction. Okay. Okay, so last little thing we want to talk about real quickly about amides. We should be able to do this in just a couple minutes. Reduction of amides. Just like we reduced esters, we can reduce amides. So there's two ways to reduce amides, and just like there were two ways to reduce esters, right? There's the R-2 equivalent way and the R-1 equivalent way. What are those two things? One, the double reduction will be lithium aluminum hydride, just like it was for esters. It's a double reduction. The single reduction will be dibol, same reagent, dibol, diisobutyl aluminum hydride. Okay. Let's show the 2 equivalent one and then the 1 equivalent one. And let's just change this. I said R minus, I mean H minus, right? We're doing reductions. Sorry about that. H and H. So we're doing H minus 2, H minus 1. So let's show the H minus 2 real quick. Okay. All right, and I'm gonna use this example. All right, so what I'm gonna do is react this with lithium aluminum hydride, and we always do a little bit of water afterwards, right? Okay, but I'm not gonna show you the product directly. I'm gonna step forward, okay? Because the product is a little weird. And all right, so what do we do first? It's very easy, just like always. We do H dot dot minus in quotes. We have H dot dot minus in quotes, right? That's our lithium aluminum hydride. And what does it do? It attacks a C double bond O. So right? Cool. What does that give us? Okay, and we also have our little AlAX2 thing up there, plus some kind of this aluminum salt. All right, and based on everything else we've done in this chapter, what is the next thing that happens? Think about it. What's the next thing that would normally happen? Electrons go up, or down, I guess in this case. Electrons go the other way and kick off the leaving group, right? And the nitrogen would be the leaving group. Well, with amides, it's a little different. With the amides, it's actually, the nitrogen kicks off the oxygen. So nitrogen is actually a worse leaving group, and oxygen's a better leaving group. So nitrogen kicks off the oxygen, and what does that give us? It gives us this thing, and this is actually a positively charged imine. We have the name for that. It's a positively charged imine called an iminium, right? Positively charged imine. Okay, but now this is actually very straightforward. H minus just does it again. Because remember that it's a double reduction, right? Or H minus attacks twice, right? So what happens when this attacks a second time? You get this. Okay? It's kind of weird. So what's the net effect of the double reduction of an amide? The net effect is just wipe off the carbonyl. The C double bond O just goes away. Isn't that cool? Kind of like how you remember like the Wolff-Kishner and stuff of a ketone, but this is a totally different mechanism. But the net effect of a double reduction of a amide is just wiping away the functional group. And it's different in mechanism than everything else in this chapter because the H minus attacks, goes on to oxygen, and then the nitrogen kicks off the oxygen as a leaving group, and then you're left with an aminium, and then the H minus attacks that. So that's that. I'll just quickly show the H minus 1 equivalent one, which is actually very easy. It's a very straightforward mechanism with dibol. So because the top was a little weird, this is a little weird, right? But the product is just the amide without the C double bond O. This is actually more like what everything else we've seen in the chapter. Let's do the same exact substrate. But do dibol. And what does dibol usually do? It's a single step reduction. Okay, so was the amide H minus does what? Attacks. All right, you get your tetrahedral intermediate, Al, X2 plus, so now it's a salt. Now what did we say about this before with the esters? It was stabilized, right? And nothing happens to it, it just stops right here until the water. Okay, so then the water protonates the oxygen. Okay, now, unlike above where the nitrogen kicked off the oxygen, now the oxygen kicks off the nitrogen. And we're done. Okay, so it's a little bit, the products are a little different. We're done now. I just want to show again what the net effect is. In a lithium aluminum hydride reduction of an amide, you're essentially just wiping away the C double bond O. H minus attacks, and then rather than oxygen kicking off nitrogen, nitrogen kicks off oxygen, makes an aminium, which is a reducible functional group. H attacks, and you're left with an amine. You go from amide to amine, yeah? Amide to amine. Now with a dibol reduction, essentially what it's doing is a single step reduction where it ends up cleaving the carbon-nitrogen bond. So H minus attacks, electrons go up, stabilized, intermediate, acid protonates the oxygen as a second step, we'll say H2O, whatever. No big, that's just not an important point. Acid or H2O protonates the oxygen, and then the tetrahedral intermediate collapses to give you the amine and the aldehyde. And so, yeah, so that's what the dibol reduction of a amide is. the diol reduction ends up with cleavage of the bond, and you get left with an amine and a aldehyde. Whereas lithium aluminum hydride reduction converts the amide to an amine. Okay, so I will show those again and review them a little bit more next time. All right, have a good weekend. So that is again the reduction of an amide by either H-2 equivalents or H-1 equivalent. Okay, see ya.